Hello AS Math, it is Mr. Knight here, coming to you with our first ever physics lesson for AS Math. Super stoked about it. Can't wait to get into it. Here's our skills for today. Here's our vocab. That stuff will come as it comes. But for right now, don't worry about answering that question. I actually need to throw this away, so I'm just gonna... I hate it when I miss. Always. It's my worst thing. I never miss. But there's a first time for everybody, I suppose. How far did I just travel from my desk to the trash can? Let's assume that that's about 8 meters. I want you to talk to a partner right now and discuss how far did I travel from my desk. Let's hear those responses. Alright, we're back. So, there's a lot of different answers to this question. Some of you guys might have said, well, you traveled 16 meters, Mr. Knight. You went 8 meters that way, you came back 16 meters total. Some of you might have said 0 meters, Mr. Knight. You did not even travel from your desk. You returned to your desk. And some of you are stuck in between those two answers. You are both correct, but we need to talk about why both of you are technically correct and then see what parameters we can make to make it so it's true. And it comes with this idea known as vectors and scalars. So a scalar and a vector, they are quantities. They are, like 8 meters per second or 4 meters. They are still quantities. The difference is vectors actually have a direction associated with them. So for example, a distance would be a scalar. I went 8 meters, and then I went another 8 meters, and that was 16 meters to get back here. So I traveled a distance of 16 meters. But if I had my direction taken into account, I went that way, and then I came back here to my original position. Well, I'm 0 meters from my original starting position. So vectors have a direction. Here are some scalars and vectors, right? Scalars, distance and speed, whereas vectors are displacement and velocity. We are really looking at distance and displacement in that last example. So my distance was 16 meters. I did travel that, but my displacement was actually 0 meters. And we're going to talk about that more in just a little bit. So I said that speed is a scalar quantity, but velocity would be the vector quantity. We'll talk about that in a little bit. What I want to talk about first is kind of our units of speed, like meters per second and miles per hour. We can write that as meters per second or miles per hour, like that. So we have some kind of distance on top divided by some kind of unit of time, and that's really what speed is. If we know the distance traveled in a given time, then we could say an object going at some constant speed, right? Its speed is equal to the distance covered divided by the time taken. However, not all speeds are constant. Most of the time it's not. Even just driving to school, I'm sure you had to stop and slow down and speed up. There are a lot of different things going on. So what we do for that is we use average speed. That is the total distance covered, so not just a particular amount, but a total distance covered taken over a total time. How long did it take you to get from your house to the school? That would be your average speed, right? Whereas maybe if you were driving up the road of Grandview before you turned, that little section, we could actually get that distance covered divided by that time taken. We can get that speed. So we can get average, we can get not averages. And the same thing works with velocity. The only difference is velocity matters with direction. So you actually can have negative velocity. You can also have negative displacement. So this is an object at constant velocity, whereas this is a velocity that is not constant. So the direction might change. The actual magnitude of it, of the value, might change. Instead of 9 meters per second, you might be going 8 meters per second in certain situations, right? So those are kind of the differences with all that stuff. So let's actually see this. All right, AS Math, let's actually see this in practice. So what I'm going to do is I'm going to look at two different cases. I'm going to pretend to be like some dude that's just jogging in place. I guess I'm not pretending, I'm actually going to be jogging in place. So no pretending at all. And what we're going to do for each case, so case 1 will be when I go this way, and case 2 will be when I'm coming back, and we're going to treat it like it's one continuous thing, but I'm going to stop at each part. What we're going to do is we're going to get the total distance, speed, displacement, and velocity for each of those cases, okay? So I'm going to start in the middle. I'm going to call this direction of the right-hand side the positive direction and the left-hand side negative. We typically do that generally when we're doing physics problems, okay? Right is positive, that way is negative, okay? So let's begin, right? So I'm some dude jogging in place, and now I'm going to go over here, and it's about 5 feet. Let's say I did that in 1 minute. So my speed is my distance traveled, 5 feet, divided by the time, which was 1 second. So I went 5 meters per second for my speed. And the distance traveled from right in the middle over here was only 5 meters. Since I'm calling this direction positive, I can also say my displacement is 5 meters and my velocity is also 5 meters per second. So in this case, the vector and scalar quantities are the same for both velocity and speed and displacement and distance. But let's continue going the other way. Let's say now, all right, I'm going to do a 180, and now I'm going to travel to the other side, okay? So now I'm over here. Let's say I did that in just 2 seconds, okay? From here to there in 2 seconds, okay? So let's see. So my distance traveled, total distance. So I went 5 feet, and then I went 10 feet, so I've gone 15 feet total. Now, my displacement is the distance from my starting position, and since it's 5 feet in the negative direction, it is negative 5 feet. So negative 5 feet. My speed was constant throughout. Let's just pretend it was. So I went 5 feet per second this way, and then I turned around, and then I came this way, okay? So we don't even need to treat it as constant. Remember, we're looking for the total. We're looking for the total speed. So I can look and see, all right, my total distance traveled was 15 feet. I did that in about 1, 2, 3 seconds. So I was still going 5 meters per second. However, my velocity, even though I'm still going 5 meters per second, I'm going negative 5 meters per second. I'm going the other direction. So the whole purpose of this was to just kind of show you guys the differences between your vector quantities and your scalar quantities when it comes to displacement, distance, and speed and velocity. So let's return to the actual problems. And start doing a few of them. Let's go. Okay, we are back. I'm actually a little worn out from that. I'm a little tired after that, okay? I just wanted to show you guys differences between vectors and scalars. And I want to show you one last relationship. This is between velocity and displacement. Like I told you guys, we can find velocity with the total distance traveled, or we can find velocity with the total displacement traveled divided by the total time. But this is another way of finding specifically your total displacement. It's this S equals VT equation. S is your displacement, V is your velocity, and T is your time. So those are the variables we're going to rock with, okay? And this is assuming that displacement and velocity are in the same direction as each other, okay? So this only works if that's the case. So let's look at skill 1, and let's actually solve for velocity now, okay? So skill 1, a car travels at 9 kilometers in 15 minutes at constant speed. We need to find its speed in meters per second. So a lot of the times, the book is going to write it like that. I am totally fine if you write this as meters per second, just like that, just like we've been. Kind of up there on the board if you saw that. Either way, I just want you aware that's what that means, okay? So, we want to actually find this guy's speed. We want to use that equation, speed equals the distance divided by the time. And it wants it in meters per second, so that's kind of a big thing. We need to convert kilometers to meters and minutes to seconds. So all we have to do is, for at least the kilometers, multiply by 1,000. So the distance is going to be 9,000 meters. And your time is going to be 15 times 60, which is about 900 seconds. And so now we could just do 9,000 divided by 900. If we do that, our speed will just equal 10 meters per second. And I'll write it like how the book likes to write it, okay? And that's all we needed to do for that problem. Now, notice this. I didn't it wasn't really that tough of a problem. But let's say I wanted to actually input these numbers in there. I would not include my units until the very end. Just as kind of a way to see, or just a way to make it easier on yourself. Now, if you ever want to check and see if you're doing something correctly, that is when the units can become appropriate, because you know that we're looking for something meters per second, and that needs to equal, well, meters divided by seconds. So you can actually put the units in without the numbers as a way to check if you're doing something correctly in physics. Totally fine. For the problem-solving purposes, save your units for the very end. Okay? Let's look at skill 2. All right, there's quite a bit to write, so feel free to take your time on that one and kind of caveman write it. Just be like, cyclists travel 5 meters per second for, caveman write it. So a cyclist is traveling at 5 meters per second for 30 seconds, then turns back, traveling at 3 meters per second for 10 seconds. Find her displacement in the original direction of motion from her starting position. Okay? So basically for this problem, we are looking for her displacement, but in the original direction of motion. So we're going to assume, and this is where we can assume things in these problems, we can actually assume that she's originally traveling in her original direction of motion, because that's what she was doing. We can call that positive. We can call that the positive direction, okay? And then when she's coming the other way, we'll call that negative. So let's actually see how to set up this problem. Alright, so when setting up these problems, kind of like I did when I was jogging in place, I did a case 1, then a case 2. I looked at these things separately because they are not constant speeds. So what I did for case 1, this is when she's actually cycling in that original direction. We can find her distance in that direction by doing S equals V times T. And then we can do it for this one as well. And then to actually find her total displacement, what we can do is, S total, that'll equal case 1 plus case 2 displacements. So what we want to do first is actually find what those displacements are. So case 1, she was going in the positive direction. That's what we called it. And so what we can do is 5 times 30, and then we get 150 meters traveled. Okay. So S1 equals 150 meters. Now, case 2. Here's where things get a little tricky. The really only thing that you need to keep in mind is now we're going the other direction. So time doesn't have a direction associated with it, but velocity does. And since it's going in a negative direction, the opposite direction, I got to make that a negative 3. So this displacement is negative 30 meters. So now all I got to do is add those together. So her total displacement was 120 meters. And that is assuming it was going from that original starting position going in that direction. Okay, so this guy ended up being positive. So she ended up going a net total of 120 meters for her displacement. Okay, so just keep your direction in mind when doing these and break it down case by case. That might help. And now our final problem, this is solving for time. A cyclist spends some of his journey going downhill at 15 meters per second, and the rest of the time going uphill at 5 meters per second. In 1 minute, he travels 540 meters. Find how long he spent going downhill. Once again, let's see what that setup is going to look like. Alright, so once again, I set it up as a case 1 and a case 2 way to solve it, okay? So we know that the total distance traveled was 540 meters. And what I'm going to do, I'm going to call T, I'm going to call that the time downhill, okay? So for case 1, this is going downhill. T is just going to equal T, whatever that is. And we're trying to find how long it was anyway. So we want to find how long he spent going downhill. So the velocity during that time was a 15 meters per second. And that guy is done. Alright, so what we can do is we can use a total distance equation to help us out. So I'm going to call this one S1, I'll call this one S2, and then together they'll make S, and we knew that was 540. So we'll start filling in what we know, and this is 15T. Okay? So then, we're going to add that to whatever this guy is. Well, we know that the velocity of that is 5 meters per second. And no opposite direction, it seems to be in the same direction, so that guy is positive. And now the time, well, we know that in 1 total minute he has traveled 540 meters. And we want it to be in seconds. So there's 60 seconds in a minute. So what we could do is, we know what time this is, and it's whatever time that was spent not going uphill. So the time spent going uphill can be related as such. It's just whatever his time was, and you subtract T from that. So we could set it up as 60 minus the time he spent going downhill. That'll give us the time going uphill. So with this one, we have 5 times 60 minus T. And now we have one variable we can solve for T. And now it's just a matter of solving for it algebraically. So we can do that. So 15T plus 300 minus 5T equals 500. 40. Almost caught me slipping. Let's go ahead and combine some terms. We got 10T. I subtract 300 over. That equals 240. And then divide 10 to both sides. So T equals 24 seconds. Okay? So typically, when we're finding time, it's going to be in seconds. When we find distance, we're going to be in meters usually, unless it specifies. And then for velocity or speed, it really doesn't matter because they have the same units. It's going to be meters per second, which makes sense. Okay, so these are like your standard units when it comes to these. Whoa, my lights just went off. That was kind of cool. All right. So this is our first lesson. You guys are going to try some of these problems and see how they all relate. I'm going to get the lights back on. All right. That's how I get the lights back on. And this is Mr. Nice signing off. Have an awesome day. Good luck on those problems.